In today's lecture, we'll study about modular arithmetic and we'll also have an introduction to what groups are. Modular arithmetic is simply arithmetic over remainders. So define it formally. Let a and b be integers and let n be a positive integer. We say that a is congruent to b modulo n, denoted by a in these three lines b mod n, if n divides a minus b. For example, we say that 23 is congruent to 8 modulo 5, 10 is congruent to 58 modulo 8, and trivially 13 is congruent to 13 modulo 3. We shall now begin with some elementary facts about arithmetic over remainders. The proof of this will be left as an exercise, but I will simply state the theorem here. The following statements are true. A is congruent to B modulo n if and only if A mod n is equal to B mod n. Second, if A is congruent to B modulo n and C is congruent to D modulo n, then A plus C is congruent to B plus D modulo n, A minus C is congruent to B minus D modulo n, and A times C is congruent to B times D modulo n. Notice over here, I did not say anything about division. I did not talk about what happens if we take A and divide it by B or A and divide it by C, even if we know anything about A being congruent to B or not. This is an important point to note, and we will discuss this later. For now, we will not talk about division. We are now ready to introduce what groups are. A group G is a finite or infinite set of elements along with a binary operation denoted by a circle with a dot inside. This just generically means any group operation that satisfy the following four properties. The first property is closure. What closure says is that if I take two elements from the group and apply the group operation to them, then I get another element which is also in the group. The second property is that of associativity. What associativity says is that the order of applying the group operation does not really matter. So if A, B, and C are group elements, then the A applied to the group operation obtained to the group operation of B and C together is equal to A group operation B, and then applying the group operation to the resulting element with C. The third property is that of identity. What that means is that there exists an identity element in G and denoted by 1 such that if I apply the identity element to any element in the group, then the group element remains unchanged. Therefore, one group element A is equal to A group element 1 is equal to A. And furthermore, this identity element is unique. The last property is the existence of an inverse. That is, for every group element A, there exists an inverse element B denoted as A inverse, such that when I apply A and B together with the group operation, I actually get the identity element. So therefore, A group operation B is equal to B group operation A equal to identity element. Some examples of groups are the set of integers with the group operation being addition. Why is this a group? First, note that closure property is satisfied. If I add two integers, I do indeed get an integer. Second, associativity is satisfied. If I add three integers, the order in which I add these integers does not matter. Third, there exists an identity element in the set of integers, namely the value 0. Adding it to any other integer does not change the value of the integer. Finally, there exists an inverse for every integer. So for example, the inverse of 3 is -3, the inverse of -5 is +5, and so on. Next, also observe that the set of integers modulo n is also a group with respect to addition. I'll leave it as an exercise for you to verify these 4 properties do indeed hold for the set of integers where the group operation is addition. We will define a few additional concepts. Finite groups are groups with finite number of elements. So for example, the group of integers modulo n with addition being the group group operation is a finite group. However, the set of integers with addition being the group operation is not a finite group. The order of the group is the number of elements in the group. Cyclic groups are groups that can be generated by a single element. That is, I can take one element and apply the group operation repeatedly to that single element and generate all other group elements. An abelian group are groups that are commutative. That is, A group operation B is equal to B group operation A for all 2 A and B that are elements of the group. We will next talk about homomorphisms and isomorphisms. Homomorphism simply says that there is a map between 2 groups G and H that preserves the group operation as well as the identity. A homomorphism with an inverse that is also a homomorphism is known as an isomorphism. In further detail, if A and B are both group elements of G and F is a homomorphism from G to H, then if I first apply F on the 2 values A and B and then apply the group operation, it is equivalent to first applying the group operation to A and B in G and then applying F. I will get the same value. Okay. An example is Z6 is homomorphic to Z3 through the map A maps to A modulo 3. Why is this true? Let us verify this. Let us look at the elements in Z6. Now let us see how these elements are mapped to Z3 through the map F. Zero is mapped to 0, 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 0 as well, 4 is mapped to 1, and 5 is mapped to 2. Now let us verify this property. If I take 2 elements from Z6, suppose I take the elements 1 and 3. What a homomorphism says is that I can apply F to 1 and F to 3, which gives me the 2 elements 1 and 0. And now I can add these 2 elements, which will give me 1 mod 3. And this is equivalent to taking the integers 1 and 3, adding them together, mod 6, which is 4, and then applying F on this. Now note that f of 4 is indeed equal to 1 mod 3. So both ways I get the same element. I leave it as an exercise for you to verify that for any two elements this indeed is true, and this means that Z6 is homomorphic to Z3. Additionally, we can also show that Z6 is isomorphic to Z2 cross Z3 through the map that takes A to the set of elements A mod 2, A mod 3. So for example, if I have an element 4, then 4 is mapped to 0 and 1 because 4 mod 2 is 0 and 4 mod 3 is 1. Again, I leave it as an exercise for you to figure out why this is an isomorphism. You can show that this map is homomorphic both in the forward direction from G to H as well as from H to G. And that will show that this map is indeed an isomorphism. This statement can actually be generalized, and there is a general form of the statement that you will be able to prove later on in this course. We will see this much later. I'll conclude today's lecture with a fun fact. Did you know that Julius Caesar actually used modular arithmetic? There is something known as the Caesar cipher, and it works as follows. It is used to encrypt messages between two participants so that an eavesdropper cannot figure out what they are communicating. For example, say Alice wants to communicate with Bob, and they share a key K with each other. Now Alice would like to send a message to Bob such that Eve, sitting in the middle, who has no knowledge about K, cannot figure out what the message that Alice sent to Bob was. So how does the Caesar cipher work? Now suppose Alice and Bob share a key and say that is 7. And the n is equal to 26 as it's the number of letters that we have in the English alphabet. Then encryption is defined as follows. I take the message M and take its corresponding value modulo 26, and I add K to it, and that is my ciphertext. Now decryption works simply by reversing this operation. So for example, suppose the plain text was et tu brute. How I would encrypt it with key 7 is, since E is equal to 5 as it's the 5th letter in the alphabet, I add 7 to it, and that gives me 12 modulo 26, and that translates to L. So E gets mapped to L, T gets mapped to A, and so on and so forth. Unfortunately, this cipher is not very secure. In fact, you may have noticed T gets mapped to T again. I can, just by looking at the ciphertext, tell that the words were such that the first word ended in the same letter as which the second word started. And this may give me some information. Indeed, it does give me information, and the cipher can be trivially broken. However, if K is random and different for every letter, then indeed such a cipher is secure. This is something known as a one-time pad, and if you're interested, go read about it.